Hello everyone. Now we are in the second half of this course. Today we are going to discuss about Neutron Porosity Logging tool. I have already discussed the basic of Neutron Porosity Log in the last lecture where we discussed about what we do in neutron logging. So we send a number of fast neutron inside the formation which can interact with the formation nucleus, and this interaction is dominated by the hydrogen atom. So hydrogen atom can slow down the neutron at a very fast rate. That's why the count rate at the detector are proportional to the hydrogen content of the formation, and hydrogen content of the formation is related to porosity of the formation. So by knowing the count rate at the detector, we can get an idea about our formation porosity. Today's lecture will be about different tool types and how they can measure the different count rates and how these count rates are converted to porosity values. So let's start today's discussion. So we will discussing about different types of tools. So how many types of tools are there? So basically all these tools differ on the type of detector. Some tool may have a gamma ray detector to monitor the capture gamma ray. Some tool may have the thermal neutron detector, and some tool may have the epithermal neutron detector. That means all these three can be monitored or recorded at the detectors. Then we'll discuss about the compensated neutron logging tool, which is one of the most common neutron logging tool in use. Thereafter, we'll discuss about the tool response and the porosity conversion, how the tool response is calibrated or converted to our hydrogen index or the porosity values. Then we'll discuss the matrix setting in the neutron log and discuss the calibration process of neutron logging tool, which is needed to convert the count rate to hydrogen index or the porosity of the formation. So these are the slumber logging tool names. So we have a GNT tool, SNP tool, CNL tool, DNL tool. GNT tool is obsolete, SNP tool is also obsolete, CNL tool is still in use, DNL tool is still in use, and then we have a APS tool. This is the latest generation of Schlumberger logging tool, Schlumberger neutron logging tool, which is nowadays available for use in different wellbore to calculate the porosity of the formation. So most of the wells in nowadays you will see either the CNL porosity tool or the DNL porosity tool will be there. So all these two tools differs only in the measurement, whether they are counting the epithermal neutron or thermal neutron or the capture gamma ray. The response is still related to the hydrogen index. So hydrogen index can be used to calculate the porosity, which will be given by this tool. For example, what are the different type of detectors? As I mentioned, we have a gamma ray detectors, we have a thermal neutron detector, and we have a epithermal neutron detectors. So all these detectors have some advantage and some type of disadvantage also. For example, if we are using a gamma ray detector to count the capture gamma ray, it will have very high DOI. But if I'm using a epithermal neutron detector, it is going to have a low DOI, because capture gamma ray are emitted farther from the source compared to the epithermal neutron. So conversion is happening in this way. Fast neutron, they are converted to epithermal neutron, then they are converted to thermal neutron, and then they are converted to capture gamma ray. So obviously if I source is here, so first epithermal neutron will be formed, then thermal neutron will get captured, and a capture gamma ray will be emitted. So epithermal neutron will be emitted near the source. That's why they will be traveling less distance inside the formation, and thus the depth of investigation will be low. Whereas the capture gamma ray will be emitted farther from the source. So capture gamma ray will spend more time in the formation, more distance inside the formation. That's why the depth of investigation of the gamma ray detectors will be high. But the capture gamma ray and thermal neutron detector, they have certain disadvantages. That's why epithermal neutron detectors are nowadays also used along with the thermal neutron detector. Generally, most of the porosity logging tools nowadays uses either the thermal neutron detectors or epithermal neutron detectors. We generally don't use a gamma ray detector to calculate the capture gamma ray count. Although in pulse neutron logging tool, which is used for the formation water saturation measurement, there we are specifically interested in the capture gamma ray count. There we only use our a gamma ray detector to count the capture gamma ray to get an idea or calculate the formation water saturation. Now, why it is that? For porosity logging tool, we don't want to have a gamma ray detector because gamma ray count and also thermal neutron count is affected by the our thermal absorber. So in the last lecture, I mentioned cadmium, boron or chlorine, they have a very high capture cross section. That means they can absorb the thermal neutron at a very fast way. So in a normal reservoir, let's say there is no cadmium, boron or chlorine. So conversion from fast to thermal neutron will be dominated by the our hydrogen index, and thermal neutron to capture gamma ray will be dominated by our whatever the nucleus present inside the formation. So, but if cadmium, chlorine and boron is present, what will happen? Conversion of thermal neutron to our capture gamma ray will be very rapid. So this way, the thermal neutron count rate or the capture gamma ray count rate is depending upon our cadmium, chlorine and boron concentration in our formation. For example, we have discussed in the last class, if count rate is low, CR, the count rate is low. That means it is having a hydrogen index that is very high. Because if we have very high hydrogen index, then the fast neutron will be slowed to the thermal neutron at a very rapid rate. Then the capture gamma will be emitted near the source. That's why the count rate will be low at the detector. But if the count rate is high, that means our hydrogen content is less. If hydrogen content is less, that means interaction of neutron with the hydrogen nucleus will be very less because the hydrogen concentration is less. That means fast neutron will be converted to thermal neutron at a far distance from the source. So thermal neutron will be captured farther from the source. Thus capture gamma ray will be emitted farther from the source. So if we are monitoring the thermal neutron count rate or the gamma ray count rate, we will have a high count rate in case when the hydrogen index is low. But what if cadmium and chlorine and boron is present? For example, what will happen to the thermal neutron population? Even if my hydrogen index is low, what will happen? Once the thermal neutrons are populated, these elements going to destroy the thermal neutron population. So what I will get? I will get low count rate at the detector. Because the moment the thermal neutrons are generated, these three elements which have very high capacity to absorb the thermal neutron, they are going to capture the thermal neutron. So the count rate of thermal neutron at the detector will be very less. So I'll think that I have a very high hydrogen index. That means I have very high porosity. But that is not the case. If there was no cadmium, chlorine and boron were present, the count rate at the detector would have been still high and we would have a hydrogen index which is less or representative of our actual formation. So this way, the cadmium and chlorine and boron can affect our thermal neutron population. Accordingly, porosity can be our overestimated. That's why the gamma ray detector and the thermal neutron detector, they are affected by our thermal absorber. So a tool which is employing this gamma ray detector or thermal neutron detector, it is affected by the salinity of the formation water as well as the presence of cadmium and boron, which may be present in the trace amount in case of our shelly formation. So in that case, I should use a tool where I have an epithermal neutron detector, which is going to count the epithermal neutron population. Since epithermal neutron population is only controlled by the how much hydrogen atom nucleus is there inside the formation. So fast neutron will be converted to epithermal neutron and only dominated by the hydrogen concentration. So if I count the epithermal neutron, the population of epithermal neutron or the count rate of epithermal neutron will be directly related to the how much amount of hydrogen is there inside the formation. So this is not going to be affected by the capture property of our formation. So cadmium, chlorine and boron cannot affect our epithermal neutron count rate. So it is the porosity calculated by a tool which is having epithermal neutron detector. It gives us a porosity value which is independent of our concentration of thermal neutron absorber inside the formation. That's why epithermal neutron porosity is often preferred when you have shale or very high saline water. But there is a problem with the epithermal neutron detector. It has shallow or low depth of investigation, but it does not give a very efficient measurement because when we are counting the epithermal neutron, we are only counting the epithermal neutron. The thermal neutron population will be removed. So basically the detector is same. At any instant when the neutrons are reaching the detector is still the same. The detector have what? A coating of cadmium around it. So it will absorb all the thermal neutron. So we are decreasing the neutron count rate. So we are getting less count rate by only observing the epithermal neutron. So that's why these detectors are very sensitive to source to detector spacing. So the tool must be designed carefully to get a very good accurate count rate which can be converted to porosity values. Moving on, let us compare the different tools which I mentioned so that you understand the effect of our formation lithology and the fluid type on different logging tool and in which condition which logging tool will give us the best measurement. For example, GNT logging tool, SMP logging tool which are obsolete nowadays, and we have either CNL logging tool or DNL logging tool. So GNT logging tool, it has thermal and capture gamma detector. So obviously salinity and thermal absorber effect will be there. They had no borehole effect detection. When you use the SMP login tool, we had epithermal neutron detector. So obviously there will not be any effect of chlorine boron or the salinity. Borehole effect, because they were pad type, the borehole effect was minimized. When it comes to CNL login tool and DNL login tool, which are used nowadays, CNL login tool have only two detectors which are pad mounted. So these two detectors are thermal neutron detector. So obviously they are pad mounted, so borehole effect is minimized. They are still affected by the salinity because we have thermal neutron detectors. So tools data will be affected by the salinity of the formation water, and if the chlorine and if the boron or cadmium is present inside our shell, it can also be affected by these rare earth element concentration. That's why the Carson charts are needed to get the true property from the CNL login tool. So salinity effect must be applied, the tool data must be created for salinity of the formation water to get the true property of the formation. In DNL login tool, which is developed after CNL login tool came into the existence, it have two thermal neutron detector and two epithermal neutron detector. So again, this is pad type, so it can minimize the our borehole effect. By incorporating two epithermal neutron detector, we can get a good idea of the porosity where these thermal absorber element are present. So when you are using the porosity calculated by the thermal neutron detector, they will be affected by what? The presence of chlorine, boron and cadmium. But when we are using the epithermal neutron detector, the porosity calculated by the epithermal neutron detector will not be affected by our these thermal absorber. So where cell is present, we can compare the epithermal neutron detector and the thermal neutron detector to get an idea about the presence of shell also, because cell have the concentration of these rare earth elements. So porosity calculation by the thermal neutron detector logging tools will be affected by the presence of shell, but the porosity calculated by the epithermal neutron detector will not be affected by the presence of shell. So this way, now you have an idea about which logging tool measure what type of count rate and how they are affected by our borehole environment. So, generally, if you are working as a log interpreter or petrophysicist, you won't be needing to apply all this correction. These correction will be applied at the well site itself by the field engineer or the person or the logging engineer who is taking all these measurement. So generally the data that is supplied to a petrophysicist is the corrected data. But you must have an idea about tool type so that if the quality of data is not good, you can identify what type of measurement this tool is having and why the quality of this data is not good. So you can find out sections where the tool data is accurate and representative of our actual formation so that you can calculate the true property of the formation. You can also do a quality check for the neutron logging tool data also. So whether the tool data is accurate or not, that must be first identified and then it can be used to calculate the property. For that, you must know what type of tool are using and what is the primary tool measurement. So let us start discussion with the signal login tool. So a signal login tool, as I mentioned, it have two detectors and it must be compensated for salinity and the thermal absorber effect because the tool data will be affected by the salinity of the formation. Tool is generally kept eccentric to minimize the borehole effect. So tool is eccentric so that there is a minimal effect of borehole environment. There is a minimal amount of mud between the tool and the formation. So what we do is that in this tool, we take the ratio of near to far count rate to calculate the porosity of the formation. We will discuss how this ratio can be converted to porosity. So the tool primary measurement is the ratio of near to far count rate. That is what the tool is going to give you, and this near to far count rate ratio is converted to porosity values. Once again, the ratio will be related to hydrogen index, which will be converted to porosity. But again, we have to define a matrix setting. So as I mentioned in the last lecture, although the tool data is primarily affected by the hydrogen content, but some other element which are there inside the formation can also contribute to the slowness of our neutron. If hydrogen is present in very less amount, then the majority of the collision will happen with the other element. So signal of other formation element is also there. That's why what is the matrix setting that you're using, that is also important. Whether you're considering that formation is made of limestone or sandstone, accordingly the signal of formation matrix would be different. So hydrogen content which we get from the near to far count rate ratio must be converted to porosity by keeping in mind the what is the my matrix of the formation. Accordingly, a proper matrix setting must be identified. Some other data about this tool: vertical resolution is around 2 feet, depth of investigation is around 1 feet, device similar to density and in flush zone. So tool mainly looks in the flush zone, not the zone beyond that. Only in case of extremely shallow invasion, the tool will look beyond the flush zone. Sometimes we need to keep this also in mind while interpreting our neutron log data, such as commenting on where the cell zone exists or gas zone exists. So let us consider the tool response and the porosity calculation. So in this figure, what we have the relative thermal neutron flux, that is how much count rate are there at detector at different distance from the source. So at a point closer to the source, that means in this region, high thermal neutron flux means high porosity. What is a thermal neutron flux? That means how much amount of thermal neutron are crossing a particular area. That is nothing but a thermal neutron flux. So if I have detector closer to the source, then high thermal neutron flux means high porosity. It is understandable because if my detector is here, let's say source is here and detector is here, and I have very high porosity, that means more amount of fluid, that means more amount of hydrogen, that means more number of collision with the hydrogen atom, that means neutron will be converted to thermal neutron from the fast neutron at a very rapid rate. That's why you can see high thermal neutron flux means high porosity when the detector is closer to the source. But at a point farther from the source, let's say when detector is here, then high thermal neutron flux means low porosity. Again, it is also understandable because let's say I have low porosity, that means what? Low amount of fluid, that means low hydrogen concentration, that means less number of collision of neutron with the hydrogen atom, that means conversion of fast neutron to thermal neutron will happen farther from the source. That's why as a detector you can see for low porosity I am getting what? High count rate or high thermal neutron flux. That means the tool data will be affected by where the detector is generally placed. That's why absolute neutron count rate is not a good indication of porosity because a number of factors affect it, and especially the spacing between detector and the source. So our interpretation will be different if the detectors are closer to the source or if the detector are farther from the source. This we need to keep in mind where my detector is placed. So where we should be placing our detector. For example, there is a crossover region. In the first region, which is also linear, which have different relationship between the count rate and the thermal neutron flux, and this is second region, which is have long spacing, which also have a relationship between the count rate and the detectors, count rate and the porosity or the hydrogen index, and again this relationship is linear. So should I place my detector here or detector here? So first thing is that we need to keep the detector in a place where the count rate versus prosody relationship is linear. So either here or here. So anywhere it can be placed. But generally we keep the detector in the long spacing region, where when the prosody is increasing, that means what? We will get less count rate. Or when the prosody is low, we will get the high count rate. So why we need to keep the detector in this region? If you keep the detector in the short region, the response will be affected by the borehole environment. By keeping the detector at a larger distance, what we are doing is that we are making the neutron to travel a larger distance inside the formation. So the effect of borehole environment is decreased, just like in the density law. So that's why all the two detectors are placed in the long spacing region where the relationship is linear, so that we can calculate the porosity. So even if we are keeping the detectors at a long spacing region, some effect of hole size, mud and the casing size, if we are running the neutron logging tool in a cased hole, will be there. So borehole effect must be corrected from the neutron logging tool data. So accordingly, we will have different types of correction chart developed for different types of tools. Each tool will have certain corrections associated with it. So you can use the correction chart developed for a particular tool to correct the tool data for our borehole effect. Although I have discussed the correction chart in the start, for example, for residual logging tool, even for density logging tool. So these correction chart, they're nothing but they record a different simulation experiment or the experimental data or the field data to give us a relationship between the borehole size, mud properties, the formation condition, the pressure temperature condition, and its effect on our log reading. So you can refer to this book, which I have mentioned also earlier. You can go to the Slumber chart book 2013 edition and see the different crescent charts developed for the senior login tool and how they are applied. Now, let us see, as I mentioned, the ratio of near to far count is related to porosity. Since we are keeping the detectors in a long spacing region, so the count rate is less affected by our borehole effect. And also we are using two detectors. So by comparing the count rate at two detectors, we can also reduce our well bore and environmental effect. For example, the ratio of near to far count rate is almost constant and it is related to the porosity of the formation. That means if I plot the ratio, that is the near count rate divided by the far count rate, it will be almost constant and it will depend upon the porosity of the formation. For example, let's say the near counter is here or near detector is here and the far detector is here. So I will have some near count and I will have some far count. So accordingly, I will get a point on this line. Then I can use a different near detector spacing and a different far detector spacing, keeping the property of the formation constant. I will have different data point. This way, I can generate different data points at different near to far counter or near to far detector spacing. So for the particular property, the ratio of near to far count rate will same. So accordingly, I will get a line like this, and the slope of this line will depend upon the porosity. So for different porosity values, I will have different lines. So this way, I can monitor the ratio, that is the near count rate at the near detector divided by the far count rate at the far detector, and I can use this ratio to calculate the porosity of our formation, because the ratio is related to our porosity of the formation. So accordingly, I can use this figure or curve to get the porosity of the formation. For example, this is the ratio of count rate at near to far detector. For example, let's say ratio is around 2. If my formation is dolomite, I will have porosity around 10. If formation is limestone, my porosity will be around 20%. If my formation is sandstone, porosity will be somewhere between 20 to 30%. That means, again, matrix setting is important because the matrix also contribute to the our count rate. So the matrix of the formation must be known accurately to get the true porosity of the formation. So if a formation is limestone and I keep the matrix setting as sandstone in this figure, so I will read porosity this value, but actual porosity is this value. So you must know the our matrix setting or the true lithology of the formation to get the porosity of the formation from the ratio of near to far count rate. So accordingly, I can use different types of matrix setting: sandstone porosity units, limestone porosity units, and the dolomite porosity units. If you recall, in the density log, we had this discussion where we were calculating the density porosity, which we calculated from this equation: phi d is equal to rho ma minus rho b divided by rho ma minus rho f. So phi d we were calling what? Apparent density porosity from the density log data, which may not be equal to true porosity. Why? Because whatever the matrix setting that we have used, if the formation is sandstone and I have presented the raw data in terms of limestone matrix setting. That means rho I am putting for what? Limestone around 2.71, but my actual formation is sandstone. Then the apparent density porosity would be wrong. Same thing also apply in our neutron data. Since the neutron data is not plotted in terms of hydrogen content, neutron data is plotted in terms of neutron porosity values. So neutron porosity value will be calculated when the raw data is presented by assuming a particular matrix setting. Let's say I choose a limestone matrix setting, then whatever the near to far count rate ratio I have at different depth, that will be converted to porosity values by keeping this middle curve in mind. So I'll only use the middle line to convert the near to far count rate ratio to our porosity values. So often you will see in the well logging report, we will have representation like this. We will have first track where you will have caliper log or the gamma ray log. Then second track, you will have the residual data or the residual log. And in the third track, you will have what? Our apparent density porosity or the bulk density of the formation, and also the apparent neutron porosity of the formation, where it would be mentioned what type of matrix setting you have used. For example, limestone matrix setting is generally very common for neutron porosity logs. So it will mention the log header what type of matrix setting you have used. Once we have necessary information about the formation, you will calculate the true porosity of the formation, which would be printed after our raw data, after phi d and phi n values. So this would be what? Phi will be what? Actual porosity of the formation, which would be computed by having the knowledge of true matrix type, true formation type, and the true fluid inside the formation. So this is what phi d and phi n represent in any well log record. Whenever you see, it is generally the raw data which is converted to porosity by assuming a particular matrix setting. Obviously, this raw data or the raw porosity data would be wrong in case I have different matrix setting. So I can show you an example of how matrix setting can affect our porosity log reading. For example, let's say I have a clean sandstone formation which have water inside it, and the porosity of this formation is around 25%. So if I use a sandstone setting, I will get the true porosity. My phi n will be 25%. But if I use a limestone setting, I will get a phi n as around 21%. This both the phi n values are correct. This phi n is with sandstone matrix setting. This phi n is with limestone matrix setting. So if you want to calculate a true porosity of the formation, this limestone matrix setting must be converted to our sandstone matrix setting. That means this phi n value must be converted to true porosity values. For that, we can use different types of equivalence curve. For this, logging companies, they develop different neutron porosity equivalence curve or different relationship between our different matrix setting porosity values, which could be used. For example, if I have a limestone measurement, phi n lm, that means neutron porosity using limestone matrix setting. If I want to convert it to the true porosity, in this case for a sandstone matrix setting, I can use the relationship which have been developed for converting the limestone porosity to our sandstone porosity. Before I show you the neutron porosity equivalence curve, I want to discuss how the neutron logging data or neutron logging tool is calibrated. So this calibration or the primary calibration is performed in a test pit which is located at the University of Houston. So count rate or the hydrogen index is calibrated against a limestone standard of known porosity. So for example, in this pit what we have different limestone block of different porosity, and these limestone blocks which have different porosity, they are filled with the our liquid or water. Since we are calibrating the tool data or the tool against the series of limestone block or different porosities, that means I am calibrating the tool data against limestone matrix. That's why you will see that limestone matrix setting is always preferred matrix setting or matrix unit to convert the neutron log data to porosity values. That means our apparent neutron porosity is always presented in terms of, in most cases, using limestone setting. Since the tool is calibrated against the limestone formation, that's why whatever the porosity that you calculate, if you apply a limestone matrix setting, so in a wellbore, if you have a limestone formation and if you use the limestone matrix setting, you'll be calculating the true porosity of the formation, provided there is no gas or shell effect. So in liquid filled limestone formation, if I apply limestone matrix setting, my log data will give us true porosity. In any other formation where my matrix is different, let's say it is sandstone, because the tool is not calibrated against the sandstone, my tool data when converted to porosity will not be equal to our true porosity. That's why we had to use the neutron equivalence curve in that case. So then we can use this porosity equivalence curve to get our true porosity for our true formation type. For example, let us say I have calculated the porosity, neutron porosity using limestone setting. Then in this curve at the bottom, I will enter with the porosity of tool calculated using the limestone setting or the apparent limestone neutron porosity. I will go up and let's say my formation is sandstone. I will go pick the sandstone and go toward the y-axis and read our true porosity if the formation is actually sandstone. This way, limestone neutron porosity units can be converted into sandstone porosity units if the formation is sandstone, or limestone porosity unit can be converted to dolomite porosity unit if my formation is actually dolomite. Here we see the two curves. One is the TNPS curve and there is a NPHI curve. These are two types of compensated neutron logging tool or the signal logging tool of Schlumberger. One is called the TNPS, second is called the NPHI. So for different tool, we'll have different neutron porosity equivalence curve. So you should be choosing the equivalence curve for intended tool only. That means for a particular tool, whatever the neutron porosity equivalence curve have been generated, you should be using only that curve, not any other curve which have been made for any other logging tool. This was only the primary calibration. We also perform secondary calibration. The secondary calibration can be performed using the local field standard in the field condition. For example, we can have large water tank which will serve as our calibration. So we can perform the secondary calibration again the large water filled tanks at different time interval to check whether the tool is still giving us the same porosity values against the known standard or not. Now the quality of the data or the calibration can also be monitored by knowing the response of neutron logging tool against a particular formation. For example, we can check the neutron logging data against a particular well site calibration. That means we can calibrate the tool before and after logging tool against known calibration to see whether my tool is recording the same data or not. We can also check the neutron logging tool response against two benchmarks. For example, in a salt formation, if I use the neutron porosity or apparent neutron porosity in limestone setting 5 NLM, it would become as minus 1.5%. Similarly, against anhydrite, if I calculate the apparent neutron limestone porosity, it will read around 0%. So this is the standard response of neutron logging tool against these two formations. Once again, the porosity cannot be negative. It is only negative because actual formation is here is matrix is salt, but we are using what? Limestone. That's why we are getting a negative porosity. And apparent neutron porosity and density porosity should always agree in clean water bearing zones where the lithology is known. That means we can take the porosity values from density log data and we can take the porosity value from the neutron logging data by applying the right matrix setting. That means rho MA intensity log or matrix in the neutron log is known to us. This must agree for both neutron logging tool and density logging tool in a clean water bearing formation. So today's lecture was about different types of neutron logging tool, how they are affected by the different formation element. So which tool will be affected by the thermal absorber effect, which tool will not be affected by the thermal absorber effect, and how Contd is converted to porosity values, how the tool is calibrated, what is the matrix setting, and why it is important to keep in mind the matrix setting of our log data. In the next class, we'll discuss the relationship between the hydrogen index and our porosity so that we can understand the tool response in different types of zone.